Hi again, and today we're going to talk about derivatives again, chapter 2, section 3. So let's begin. Returning to this tangent slope problem from the first section, let's look at the problem of finding the slope of the line L. So we're talking about this line here, which is the tangent line at the point 2, 4. Okay? That's what this is talking about in the graph below, which is tangent to f of x equals x squared, which is saying that this function here is y. This is y equals x squared. So we could estimate the slope of L from the graph, but we won't. Instead, we'll use the idea that secant lines over tiny intervals approximate the tangent line. That's the basic idea behind calculus, is taking little tiny things so that we can approximate bigger things, okay? So this other graph on the right basically is saying, okay, well, if I have a point here, well, this is at 2.5, and I have a point here at 2, I can kind of estimate because they're getting closer, right? And if I were to get close, basically, if I were to get closer and closer, like, what if I said, okay, now let's move it to 2.25, right? Then I'm closer. And then what if I move it to 2.1, right? Then I'm closer. And that's the idea of the derivative. We're gonna use the limit that we learned, which, remember, the limit is something approaches something else. And we're saying that there's this point out there and it's approaching the point that we want to find the slope at, which was the instantaneous rate of change. And as it gets closer and closer, it doesn't have to be that number. It can be just a little bit off from that number, and we can determine the limit, right? The same is true here. We can do the same thing and determine the derivative. All right, so notice here, as x gets closer and closer to 2, so let's say the limit of x squared as x approaches 2, right? That's what that's doing. We're getting closer and closer to 2. And we're saying, well, that equals 4, which, notice, this is getting closer and closer to 4. Okay? So that is the slope of the line through some point really close to 2, 4 and 2, 4. And this is getting closer and closer to 4. And this is getting closer and closer to 4. The only difference between the right and the left is we're taking the left-hand limits, basically, and the right-hand limits, right? You see, just like we talked about in the last class. And we're coming into this graph. So we're coming into this graph from this end, and we're getting closer and closer to 2, because we have a secant line and we have a tangent line. So if I say, okay, that's 2.5, and I'm coming in to 2 from the right. So basically, we're saying the limit as x approaches 2 from the right of my function x squared. Okay? And we can see that that's what's going to happen. We're going to get close. We're going to pick points closer and closer, and we could calculate them on a table, and we can find the slope. But I promise that's not how we find derivatives. This is more just explanatory, okay? So if I want to find the slope of this secant line, notice I have one point at 2 and one point at 2 plus h. I don't know what h is, so I don't really know what the y value that goes with it is. But I know that I have a point here, and that point is 2, 4. X equals 2, y equals 4. My function is y equals x squared. Now, what does this 2 plus h mean? Basically, what this 2 plus h means is very similar to what we have here. We picked a number 2.5, which is the distance between those two numbers from here to here is 0.5. So for this graph, this would be my h. But what if I wanted it to be smaller? Then I would have to keep changing the numbers, which is what we had to do in this slide. We kept putting in different numbers all the time, right? We have another way we could do it. So what we're going to do is we're going to say, well, let's pick some number where the distance between these 2 points is h, and I can make it as big or as small as I like. So I would have an ordered pair here of 2 plus h, and then I have my y value. So I know that y equals f of x, which equals x squared. So first thing we're going to do is we're going to say, well, if this is an x, this is an x, and that's my initial function. Okay. Now, if I plug in 2, I have 2 squared, which is equal to 4, which is the same as this point right here. Another point x, which is 2 plus h, and here we have 2 plus h. So my ordered pair is my x value at this point is 2 plus h. My y value is 2 plus h quantity squared. And I already know my point at 1. So this is my point at 2. So I'm going to call that point 2, that point 1, and I'm going to plug in my values. I get 2 plus h quantity squared minus, so that's y2 minus y1 divided by x2 minus x1. Okay, we might be getting somewhere. This is equal to, well, this right here is not 4 plus h squared. It's a common mistake. That's why I'm pointing it out. This is really 2 plus h times 2 plus h. The exponent only affects what it's next to, and here it's next to the parentheses. And then minus 4 divided by, well, I can cancel this 2 with this minus 2, and I really just end up with h in the denominator. So let's continue. I'm going to FOIL those 2 plus h's together, multiply them together, and get 4. First times first, outer times outer, inner times inner, last times last. So this is that multiplied out, minus 4 divided by h, which is equal to, now I have 4 plus 4h, combining like terms, plus h squared minus 4 over h. And notice again, I can cancel 4 with negative 4. So this is going to equal 4h plus h squared divided by h. And I'm going to factor an h out, and I get 4 plus h times h over h. And I can always cancel factors. So h is a factor, and h is by itself. And what I end up with is 4 plus h. All right, now let's take it to the next step. What is my goal? My goal is to find the derivative, which is the slope of the tangent line, which is only really at one point. So what if I make x really small? I just make it smaller and smaller until I make it almost 0. We could write the slope of the tangent line is equal to the limit of m, because m is my slope, as h approaches 0, which is equal to the limit of 4 plus h as h approaches 0. So this is why limits are important, because what I'm doing is I'm making that distance between 2 and the point next to it almost exactly 0, right? Because h is approaching 0. So I can say this is equal to, if I plug in 2 for h, this is equal to 4. And now I found the slope of my tangent line. So I said it was 4. My table said it was 4. And this is this is a little more algebra, but we can really actually find the value. Okay? All right. The tangent line problem and the instantaneous velocity problem are the same problem. In each problem, we want to know how rapidly something was changing at an instant in time, which would be the same as saying at one point. And the answer turned out to be finding the slope of the tangent line, which we can approximate with the slope of the secant line. But we don't want to approximate this. We want to know exact values. So this idea is the key to defining the slope of the curve. And now we have a little bit of formal calculus. So let's go through them one by one. The derivative of a function f at a point x comma f of x is the instantaneous rate of change. Okay, so the derivative is the instantaneous rate of change. Very important. The derivative is the slope of the tangent line to the graph at a point. Whatever the point is. If we don't know the point, we just say x comma f of x. These are saying the same thing, but in different ways. The derivative is the slope of the curve f of x at the point x comma. So it's the slope at the point x comma f of x. The function is called differentiable at x comma f of x if its derivative exists at that point. If it doesn't exist, it's not differentiable at that point. Next, there's a lot of different ways that we can say derivative. Derivative of y equals f of x with respect to x, I know you don't understand that, I will explain it, is written as, we can use this notation, f prime of x. So we say f prime of x, or we can say y prime. When we see that little apostrophe, we know it's the derivative. This says the derivative of y with respect to x. So whatever goes on the top is what you're taking the derivative of, and what goes on the bottom is what you're taking the derivative with respect to. I know you don't understand what I'm saying yet. Don't worry, you will. Or we can say the derivative of f with respect to x. That's what this says. The derivative of f with respect to x. These all these different ways really mean the same thing. The notation that resembles a fraction, which is what I just talked about, is called Leibniz notation. Notice that the numerator, the top of the fraction, tells me what I'm taking the derivative of, and the bottom of the fraction is giving me my independent variable. In this case, it's x. It looks like a fraction because the derivative is a slope. In fact, this is simply the change in y over the change in x. How do we actually talk about finding the derivative? So we can say the first one, we can find the derivative of a function. We can take the derivative of a function, or we can differentiate a function. Again, all those mean the same thing. We use an adaptation of dy dx notation to mean find the derivative of f of x. So the derivative of f of x with respect to x is going to equal df dx. So let's draw a graph again. And we can use still the same parabola. So let's say this is 2 and 1, 2, 3, 4. So this is going to be my shape right here. Now, I'm not actually going to use numbers this time. I'm going to say I want to find the derivative of this function, which I don't know what it is. Let's say I don't know what it is. Actually, let's draw it like this so that we don't know. So let's say I'm going to draw a graph. And the graph looks like this. Okay? And we want to know what the derivative is, or we want to know what the slope of the line is, or we want to know the slope of the tangent line at this point, which would be something that looked like this. But do I know what this value is? I do not. I'm going to call it x. And I'm going to say right next to it, we're going to say this is x plus h, right? And the distance between those 2 points is h. And that means I have another point here on the graph. And that would be a secant line. The purple would be a tangent line. So if I were to take this, so I'll say this is x comma f of x. And I'll say this point here is x plus h, comma, f of x plus h. Okay. Then my slope is, if this is my 0.2 and this is my 0.1, I have f of x plus h, which is y2 minus y1. Look at this. F of x plus h minus f of x. So if I were going to say y2, I would say f of x plus h. Y2 minus y1 divided by, and I'll take these away, Let's just get rid of this. We'll bring it back in a minute. Because what do we have? We have x plus h minus x. Well, the x's cancel, and I end up with h. So let's bring it back. And we'll erase all this. That's how that becomes h. Because that's y, x2 minus x1. And when I do the math, when I add them together, I get h. Because the x's cancel. So this is literally our definition of the derivative. This is how we find the derivative. Now, we do have some formulas that make it a lot easier. Don't worry, you don't have to do this every time, but someone had to do this for every function that we know the derivative of. So, practical definition. The derivative can be approximated by looking at an average rate of change or the slope of the secant line over a very tiny interval. We've talked about that a lot. The tinier the interval, the closer this is to the true instantaneous rate of change. The slope of the tangent line or the slope of the curve. So this right here, so this part right here, let's see, this part right here is the average rate of change between 2 points. When I add this limit on, as h approaches 0, that's what that says. As h approaches 0, that means those points are becoming the same point, but not exactly. That is what is happening. We're making everything really tiny so that we're using 2 points that are so close together, it looks like 1. The derivative can be approximated by looking at an average rate of change or the slope of the secant line. That's what I said here. This part right here is the average rate of change or the slope of the secant line. But when I put this limit here, that is giving me over a very tiny interval. The tinier the interval, the closer this is to the true instantaneous rate of change, which is the same as the slope of the tangent line, which is the same as the slope of the curve at that point. Okay, so we're going to use this a lot, don't worry, but I'm hoping that you're understanding. Looking ahead, we will have methods for computing exact values of derivatives from formulas soon. If the function is given to you as a table or a graph, you will still need to approximate this way. The derivative as a function. We now know how to find, or at least approximate, the derivative of a function for any x value. This means we can think of the derivative as a function as well. The inputs are the same x's, and the output is the value of the derivative at that x point. So let's look at this example. We have this graph, y equals f of x. They're not telling us what the function is. We can use the information in the graph to fill in the table below, showing values of f prime of x. Remember, f prime of x is the derivative of the function, which is the same as the slope of the tangent line. So let's look at it. Here we have our x value. So at 0, see the red line? We want to know what the slope of that is. So if we take a ruler, and we don't have to always take a ruler, but for this one, I'll take a ruler. We can kind of see that it's 1 over 1. At x equals 0, y equals 0, but the slope is going through 0, 0, and 0, and 1, 1. So we would have up 1 over 1, slope is 1. Okay, then we're here at the top. And we're looking at that line, which is the tangent line there at the curve, remember, where it turns. And that's a horizontal line, slope is 0. And at 3, we can also see there's a horizontal line and the slope is 0. So these two are the horizontal lines for the tangent line, because remember we talked about this earlier, when it's at the maximum or at the minimum, we have this the zero slope of the tangent line. And then basically this is +1, I just showed you. So this right here, we can see it's a negative value. And if I follow this up, basically I have rise over run. It's going up 1 and to the left 1. So the slope of this line is going to equal 1, but it's negative, so it's -1. Anytime it's going down, it's -1. Check. At 3.5, there's another line here. And we're wondering, let's see what the slope of that line looks like. So it's kind of going like this, isn't it? Well, if I'm starting at -1, I'm going up 2 and over 1, which gives me my slope of 2. And so on. We're also looking at 4. So there's another slope here of a tangent line at 4. And if I extend it, it looks like I'm going up 1 and over 1. So my slope is 1. This is all just an estimate still. And then at 5, y equals f of x is 2. So f5, this is my tangent line. If I extend it out, it looks like, if I start here, I'm going up 1 and to the right 2. So that means we get 1/2. And that's how you can use a table to basically estimate your slopes. So here we have an example, example 2, and it says shown is the graph of the height of a rocket at time t. So in seconds, this rocket is going up and it's rising at this certain rate. Sketch the graph of the velocity of the rocket at time t, which the velocity is the derivative of the height function, right? If we have height, the derivative is slope, which would be height divided by time, which seems a lot like distance over time, which we said was velocity or rate. Now, if I were to start drawing little tangent lines, I could see that this has a slope that looks like this, and then this right here, and then maybe here we would have a slope that looked like this, and eventually we would have, at the very top, have a slope that was horizontal. And then now, after that, what's happening? It's starting to get negative. And it's going to keep getting more negative. So it's going to keep getting more negative, because notice the slope is changing as I go around, isn't it? Let's say I'm right here. That would be the slope of my tangent line. So it's kind of forming this line. And notice here at 5, I said my slope is horizontal, so my slope is equal to 0, and that means my velocity is equal to 0. Okay? But then all of a sudden, at the very end, it just abruptly changes. to a different slope. It doesn't slowly change to a different slope. If I erase this line, you can see there's something very abrupt happening right here. That is because the slope is changing drastically at that point. When we want to find the derivative of something, we often say that the curve has to be smooth and continuous. Say it looks like this, right? You can see how dramatic the change is right at this point right here. That point is not differentiable because you can see which one is it. But it's differentiable everywhere except at that point. So we have poles, and then we have the slope of the rest of this line. Okay. So that's kind of how we estimate slopes. All right. Okay, well, thank you so much for watching, and we'll revisit each other at 2.4.